So the final question on this non-calculator November 2015 paper is question number 22, and we finish with another quality of written communication question, and this question involves both circle theorems but a difficult version of the topic where we're asking to have some kind of proof. We're told that triangle BCD, so if we draw that in now, triangle BCD, which is here, is similar, and the similar concept in maths means that they're scaled up and down versions of each other, so they're going to be proportionate but the angles are going to remain equal, to triangle ECA. So if we draw that one in separately, triangle ECA is the large triangle which also incorporates the smaller one that we've just drawn round. So we've got two triangles there, and we're going to have to somehow prove that they are similar shapes, and to do that we're going to have to prove that their angles are equal. So if I draw those two triangles out, I've got the larger triangle here, which is labelled in the diagram as ECA, and I've got the smaller triangle, which is in the diagram labelled as B, C, D. The first thing I'm going to do is I'm going to look at what circle theorems this question might incorporate, and we can see here that A, B, D and E are points on a circle, so I have a cyclic quadrilateral, and we know that the rule of a cyclic quadrilateral is that the pairs of angles that are opposite each other, so this one here and this one here, total 180 degrees. So those two make 180, and we know that separately this one here and this one here total to make 180 degrees. I'm sure that's going to be relevant information later on in the question. So let's try and get on with proving how these two triangles are similar, i.e. they're a scaled up version of each other. The first thing we can do is we can note that here and here we have a common angle. So in the larger triangle, triangle ECA, we have angle, so let's look, we have angle ECA is equal to, in the smaller triangle, triangle BCD, angle DCB. So angle DCB. So this angle here is equal to this angle here, so we have common angles. So that's the first stage of our proof. We can prove that one of the angles in each triangle is absolutely identical, and now we're left with the other two. So let's have a look and start with this angle down here, which is this angle here, which we're going to label as angle AEC. Angle AEC, this one here, or up here, this one here. Now we know that angle AEC with angle over here, ABD, totals 180 degrees. So we could say that angle AEC plus angle ABD equals 180 degrees, because of this concept of angles in a cyclic quadrilateral. And what we can also say from our diagram up here is angle ABD, which we've already talked about, angle ABD plus angle DBC, so the one in here, are going to also make 180 degrees because they form a straight line. So we can also say angle DBC equals 180 degrees. Now, they again have a common shared angle, which is angle ABD. So we can now say that angle, let's just summarise that, we can now say that angle AEC, which is this angle here in one of our similar triangles, is equal to angle DBC, which is angle DBC BC, this angle here. So we now have a second pair of angles. So the first pair are equal, the second pair are equal, and that's going to leave us with our third and final pair of angles which we need to prove are equal. So we're talking about this angle here, and we're talking about this angle here, and we're going to use exactly the same theorem as here. So we're talking about angle EAC, so this one, and we're talking about angle BDC, angle BDC, so this one. And once again, these two form a straight line, so making 180. These two are angles in a cyclic quadrilateral, so make 180. So if we take out the common angle, we're going to be able to say that angle EAC is equal to angle BDC. And obviously we would just explain that in a bit more detail using the circle theorem from above.